Welcome to the notes on factoring binomials, and in this one we're going to focus on the difference of perfect squares. So let's take a look at that difference of perfect squares. This phrase right here. All right, difference, that means subtraction. So in all these binomials, there's going to be a subtraction sign. So if you see a subtraction sign, you got to be thinking difference of perfect squares when we're factoring binomials. And then perfect square, what does that mean? Well, those are the numbers when you take the square root, like 16, it's a perfect square. Because when you take the square root, it equals 4. All right, there's several perfect squares out there. I think you guys are familiar with them. You know, like one that's not a perfect square. A lot of people think square root of 2. That's not a perfect square because when you square it, it's not a whole number. So that is not a perfect square. 9 would be another example. Square root of 9 is 3. All right, there's several out there. Even then, when you get into variables, a squared is a perfect square because when you square root it, it's a, because a times a, the same number equals a squared or x squared, or whatever the case might be. So keep that in mind when doing these problems. Let's get to some examples. So remember, what happens when we take x plus 3 times x minus 3? Well, when we FOIL that out, or distribute it, we take the x, we times it by the x minus 3, we take the plus 3, we times it by the x minus 3, we get x squared minus 3x. All right, when I go here, then plus 3x, and then that's a minus 9. What happens to these two terms, the plus 3x and the minus 3x? They cancel out. It's 0. So we're left with x squared minus 9. Notice that right here. If we end up with x squared minus 9, well, we started at x plus 3, x minus 3. This right here is an example of a difference of perfect squares. X times x is x squared, minus 9 is 3 times 3. So that is the pattern that we're going to see. One's going to be positive, one's going to be negative. So let's take a look at some examples now that you know what it looks like. Here we go. All right, negative 25 plus x squared. The key to this problem is to rewrite it. All right, we want the x squared in front. We don't want that negative. So watch what happens when I rewrite it. Because remember, I can switch the order. 2 plus 3 is the same as 3 plus 2. All right, so I'm going to call this one x squared minus 25. The signs stay the same. At this point, this is a difference of perfect squares. So my final answer, I know it's going to be double parentheses. What's the same thing that multiplies into x squared? Well, it's going to be x times x. I know one's going to be positive, one's going to be negative always. What's the square root of 25? 5 and 5. Okay, let's take a look at some more examples. All right, again, subtraction sign, binomial. You're thinking difference of perfect squares, but now we got some a squareds and some b squareds. That's okay. Let's just follow the pattern. We know it's going to be double parentheses. We look at the first term. What's the square root of 25? Well, it's going to be 5 and 5. We know it's going to be a plus and a minus. Now, but we've got an a squared, so it's 25a squared. So I need a 5a times a 5a. You know it's the same term. All right. Then I've got minus 9b squared. Well, I know the square root of 9 is 3 and 3, but since it's b squared, I need a b and a b. So notice, same two terms, same two values in each set of parentheses, but one's got a positive, one's got a plus, one's got a minus. You can write the plus minus in either order. It does not matter. Okay, here we go. Oh, now we just got some variables. Okay, it's okay. Let's two terms. Those are still perfect squares. All right, x to the fourth. Remember how exponents work. When we multiply, we add the exponents. So same thing that multiplies in x to the fourth must be x squared, x squared. This time I'll put the minus first, then the plus, because again, order doesn't matter. What's the same base and exponent that multiplies into y6? Well, that's got to be y to the third, y to the third. There's your answer. Okay, next one. All right, this is a special one. Notice, this is a plus sign. So it is not the difference of perfect squares. So this is something, believe it or not, if we try to factor it out, we can't. So this is not factorable. All right, or in the My Math Lab, they'll say that it is prime. You can't factor, all right? We've got two perfect squares, x squared and 4, but it's not the difference. So if you see that plus sign, it's not, watch out for that. It's not factorable. All right, let's take a look at one more. This time it's got a negative in front. So what we need to do for this one is we need to factor out a negative 1. So the first thing I want to do is I want to rewrite this by factoring out the negative 1. I take out the negative 1. All All right, so if I factor out a -1 from -49, I'd still be left with a positive 49x squared. And if I factor -1 out from the positive 16, well, again, that switches the sign, so that becomes minus 16. So now I've got a difference of perfect squares. So my final answer is going to look something like that. I'm going to keep that -1 on the outside. I'm going to put my two sets of parentheses. I know it's going to be plus minus, all right, because the signs are always switched. And then I look at the 49x squared. What's the square root of 49? Well, it's 7 and 7, but I've got an x squared, so I know it's got to be 7x times 7x. And then I look at the minus 16. I know that's going to be plus 4 minus 4, and there is my final answer. So there is our lesson on factoring binomials, especially when they're all most of them are going to be difference of perfect squares.